And I'm going to share my screen. And when I share my screen, what I'd like to do first is just show you a couple of things that I added to Blackboard. One over here in that left-hand menu, I added a link for my office hour. And those are the scheduled office hour times, Monday, Wednesday, Friday at 9, Tuesday and Thursday at 11. I had thought that maybe if I had them as a link in that left hand, it might make it easier for you folks to get there. Notes, I have uploaded in here the YouTube video from last class and the notes from last class if anybody needed them, and also learning modules content, that link to submit the work. A lot of people submitted me pictures of something that they wrote. Some people wrote me a sentence, a paragraph about themselves, which was great to read. Some people just sent me a picture of their notes. That's fine too. I just want to see that you can upload a photo of something that you've handwritten and that I can open what you uploaded and then I can read what you uploaded. So, you know, if you get a chance to do that, if you have not yet done so, I would appreciate it. Then next, I think I sent everybody who had not yet registered for my math lab reminder to register for my math lab. If you're holding off waiting for financial aid or a paycheck or something like that, please get in right away using that 14-day free trial. If after that 14-day free trial, you have difficulties, we'll cross that bridge then, but there's no reason for you to wait on starting the homework. Before we get started picking up with the notes from where we left off, again, folks who were early heard me say it. I just want to give everybody a heads up. I forgot to hit record on the notes for my Tuesday, Thursday class, and so I am going to post this recording for the Tuesday, Thursday. And also I apologize, somebody made me aware of the fact that, and I meant to tell you guys it's the first day. For you, my math lab, it's gonna say Tuesday, Thursday, don't worry about it. It was a problem with the title linking, and the dates should be right, everything should be right, it's just the title that's wrong. And I apologize for that. Before we get started with the notes, does anybody have questions on anything? Homework, notes, policies, how to do, what to do, where to find, any questions at all? If not, the introductory assignment is due on Monday. That first assignment for section 1 is due next Friday. Today we're going to be looking at tests and inequalities. Last class, we left off with that order of operations. And with that order of operations, we said, it's please excuse my dear Aunt Sally or PEMDAS. The P said we do the parentheses first. The E says we do exponents next. The M and D go together in one step as they come left to right. That's multiplication and division. And then the A and the S as they come from left to right, all A and S, pardon me. It would, sorry about that, folks. That's what happens when I rush. A and S is the addition and subtraction, all one step as they come from left to right. And if I remember correctly, that was where we had left off. So let's look at an example. Let's say I have 4 plus 2 minus 5 plus 6. And again, to evaluate this, addition and subtraction are treated equally. We do them in the order that they come from left to right. So 4 plus 2 would be 6. 6 minus 5 would be 1. Plus 6 would give me 7 for that. Is everybody okay with a hierarchy that addition and subtraction are created equally? And again, the other thing that I don't remember if we stressed was the idea that if we have a rational expression, which is a fancy way of saying a fraction, that there are parentheses around the numerator and parentheses around the denominator that aren't always shown. So let's look at a couple more examples, making use of the order of operations. I'm going to ask you folks to please simplify the following: 2 times negative 2 minus 4 times negative 2 over 5 minus 8. And I'm going to shut up for a minute and ask you folks to simplify that using your order of operations. How's everybody doing? Does everybody have that? Or do I need to wait another minute? Is anybody else getting as a final answer 4/3? Do we need to add detail?
Wait, how are you getting 4/3? Because I'm getting like 2/1.
Okay, let's look at it and see. Order of operations, they are not written, but you have to realize there's an invisible parentheses around the numerator and an invisible parentheses around the denominator. So we want to simplify first the numerator. In the numerator, we have to follow our order of operations. And so order of operations, no parentheses inside, no exponents, so we're going to multiply. 2 times negative 2 is negative 4. Minus 4 times negative 2 would be minus negative 8. And then finishing in the numerator, negative 4 minus negative 8 would give me, I apologize, I made a sign error there. That should be negative 4/3, I'm sorry. It gives me a positive 4. And then in the denominator, 5 minus 8 is negative 3. So that gives me 4 over negative 3. And with a fraction like that, if there's a negative anywhere in one part of the fraction, we have a little bit of liberty. We can write that as positive 4 over negative 3. If we wanted to, we could put the negative sign in the numerator, negative 4 over 3, or we can put the negative sign out in front of the whole thing. Better, Rizwana?
Yeah, thank you.
Okay, now in terms of something like that, if you're doing the homework in My Math Lab, a lot of times they see you to write your final answer as the ratio of integers in simplest form. And that's just a fancy pants way of saying, leave it as a fraction. If you can reduce the fraction, fine, but leave it as a fraction. Most often, we will not want things converted to mixed numbers or decimals. So usually you're going to leave it as that fraction. Instead, if it asked for a mixed number, it would be negative 1 1/3. And if it asked for it as a decimal, it would be negative 1.3 repeating. And if they asked for it as a decimal, they might tell you where to round. But if they don't tell you where to round, don't round. But again, most often we want to leave it as that improper fraction. So let's try another one. This one's a little bit more involved. And again, I'll give you guys a minute. Let's look at 8 minus 3 parentheses negative 2 parentheses 5 minus 7 close minus 5 parentheses 4 minus 2 squared close close. Again, realize they're nested parentheses. Make sure your parentheses to match up. These match with each other. These match with each other. And these outer ones match with each other. So I'm going to shut up for a minute and ask you folks to tell me what you get for this one. While you're working, I'm going to do a little bit of housework. Michael, I saw that you came in late and I got you in attendance. I also saw somebody else that came in late, but I have to apologize. I forget who.
Yeah. So I went to the bookstore. I mean to interrupt, but I went to the bookstore and because I got an email saying that my account was on hold because I didn't pay the bookstore $74 for the book, and then I went there to buy it or pay for it, and they said that it should have been already included in tuition, and so I don't know what to do. And
Huh. Can I talk to you with you about that after class?
Yep.
All right. And but who else came in late? Somebody came in after
I came in late. I'm sorry.
Okay, thank you. I remember seeing somebody come in, but I couldn't remember the name, and I want to make sure that I got you. Thank you.
Thank you. Welcome.
How are you folks doing with this problem? Anybody got an answer?
Negative 45.
Negative 45. Okay. Anybody get anything different? Negative
I got -4.
4, and I think I thought I heard somebody else say negative 4. I also got negative 4, so let's take our time going through this. Order of operations says parentheses first. So we're going to look inside these parentheses. Inside the parentheses, we do the other parentheses. So in here, within this problem, this part, that 5 minus 7 is negative 2. So that's negative 2 times negative 2 minus over here inside these parentheses, we've got to do that exponent first. So 2 squared is 4. So in those parentheses, I have 4 minus 4, which is 0. So that becomes 5 times 0. Now inside those parentheses, we multiply. Negative 2 times negative 2 is positive 4. 5 times 0 is 0. And so in those parentheses, I have 4. So now what I've got is 8 minus 3 times 4. Order of operations, I multiply first. 3 times 4 is 12. So that's 8 minus 12, which gives me that negative 4. And I was a little bit lazy. The front of this problem didn't disappear. It's just that I was only focusing on what was in the parentheses. Better? Let's try one more. Let's try 6 plus 2 times 2, all of that in parentheses squared, over 4 minus 9. Let me know when you guys are close to done. Is there anybody else getting a final answer as -20?
Yeah.
I
Or-
got -20.
Good. Do we need to add detail to get to that -20, or is everybody okay?
So far.
Yeah, I need you to add detail. Shoot, I need it.
Okay, so order of operations is going to start inside the parentheses. Inside the parentheses, first I'm going to multiply. So that becomes 6 plus 4 squared. And again, we still have work to do inside the parentheses. 6 plus 4 is 10. Oh my heavens, I'm so sorry. I at least I got the headphone, the microphone off before that happened. I'm so sorry. And then 10 squared is 100. In the denominator, 4 minus 9 is -5. And then 100 divided by -5 would give me that -20. All right? Another way you might see these questions asked is sometimes you're asked to evaluate an expression for a given value, pardon me. Evaluate an expression for a given value. And so an example of something like that might be evaluate 9 plus 3 parentheses x plus 2 close parentheses cubed when x equals 4. And is everybody comfortable with the idea that over here we're given a value to substitute for the variable? So what we're going to do is we're going to substitute value for the variable. And then simplify. But when we simplify, always remember your order of operations. Dasser and Sally. I know there's some people that if it strictly says it's an order of operations problems, they get it right. But then if it's simplified, they forget to apply it. That's got to apply for everything complication that we do. But here we're given that x is 4. So in the original problem where there was an x, we're going to substitute 4 or replace it with 4. And is everybody in the room comfortable with that idea of substitution?
Yeah.
Okay, so then going through and simplifying with our order of operations, that's 9 plus 3 times parentheses first, 4 plus 2 is 6 cubed. Then exponents, 9 plus 3 times 6 to the third is 36 times 6 is, oh heaven, help me, 36 and 180 is 216. Then multiplying 3 times 216 is 648. And 9 plus 648 is 647. No, it's 657. What was I thinking? 657. Sorry about that, folks. Everybody all right with that one?
Isn't it 9 plus 3 is 11 times 216?
Order of operations. Remember parentheses, then exponents, and you multiply and divide before you add and subtract. So if that
Okay.
we add.
So it's 216 times 3.
Yeah. And then add the 9.
Cool.
Next, let's evaluate x squared minus 6x plus 2 for x equals 7. And I'm going to give you folks a minute to do that. Is there anybody else getting 9?
Yeah, I got 9.
7 squared is 49. 6 times
49.
7 is 42 plus 2. That addition and subtraction as they come from left to right, all one step. So that's 7 plus 2, which takes me to 9. And one more of these, let's evaluate x squared minus 8 times parentheses x minus y. Well, notice this time we've got 2 variables, so we're going to have 2 values to substitute. X equals 8 and y equals 1. And oh my heavens, something very weird just happened at my house. The sun came out. Really bright and sunny. And so the sun is shining right now on the surface. And last semester I learned that if the sun shines on the surface, it overheats. So while you guys do that problem, I'm going to rearrange my desk.
Mark, I think you're unmuted, just so you know.
What's up?
You're unmuted, just so you know. I don't know if you knew.
Okay.
All right, I got 8.
Anybody else get 8?
Yeah, 8.
8? Life is good?
I don't know about that, but we're chilling.
Hold on.
You know, where would you rather be than right here,
Got
right
8.
now? Life is good. We're doing math.
I mean, Cancun seems pretty nice right now.
The sun's out. The sun's out.
The sun never goes away in Cancun. That's the nice part.
No, I think down there they do crazy things like get hurricanes. Just
7.
a second. I'm sorry for all these interruptions. My phone fell out of my pocket and was on the floor. And so I just had to hang up on somebody. I don't know whom. So where we're going next is the idea of sets. And there isn't a lot on sets in this course, but there are some things that make use of set notation and some set operations. So I want to make sure that we're all on the same page. We're going to define a set as a well-defined collection of objects and in this class, because it's an algebra class, we're going to mostly be working with number sets. In my contemporary math class, instead of spending 20 minutes on sets, we spend a whole unit on sets. And we look at sets made up of all sorts of different things. There's a lot of things that can be done with sets. Here we're going to mostly focus on number sets. And one thing that you have to be able to do is look at them in different ways. Sets can be shown in 3 ways. One way is by roster. With roster, what we have to do is we have to use braces. And braces are those kind of funny looking parentheses on your keyboard. I think if you're putting an answer in your MyMathLab, the braces should show up in the toolbar as an option if they're needed. If you're doing something by hand, please make sure that, I mean, I don't take off for artistic merit, but they're not parentheses. Make sure there's some sort of squiggle in the middle of your parentheses. You list all the elements of the set. You put commas between the elements. And you don't repeat the elements. For example, I could have a set, I'm going to call it S, and it might contain 1, 2, 3. And so I'm in braces. I've listed my elements. I've put commas in between, and nothing's written down more than once. Another example, I could have T that contains 1, 2, 3 without commas. Did you see how important those commas are? This first set has 3 numbers in it. The second set has only 1 number in it, number 123. When we look at sets, whether they're by roster or any other way, there's a symbol that you're going to see. And that symbol looks something like this. And when I look at that, I see an oddly shaped E. Does that look like an E to anybody else? The fact that it looks like an E reminds me that that means element of. And I use that to state that something is in the set. So for example, if I look at that set S up above, I could say that 2 is an element of S. When we do this, the element has to go in front of the symbol, and the set has to go after. This is read as 2 is an element of set S. And it's a fancy pants way of writing, yeah, 2's in there. Instead, I might say that 2 is not an element of T. 2 is not inside set T. T only contains 1 number, 123. So when it's crossed out, it means not an element of. So far, so good. If so, I'm going to turn the page. Everybody caught up?
Yep.
Then the next place we're going to go is an empty set. And an empty set is a set that has no elements. Which I think is sort of what the name implies. If it's empty, there's nothing in there. When I have an empty set, I can show it as my braces with nothing in between. Is that picture what you see when you hear an empty set? There's nothing to put in that roster. It can also be called the null set. Nope, null begins with an N and not an M, by the way. The null set. And another symbol for an empty set, the null set is at 0 with a slash doing. So the empty set, braces with nothing in it, and the 0 with a slash through it, both mean the same thing. The empty set is equal to the null set. You're going to use that type of notation, one or the other. If you're solving an equation and it has no solution, the solution set is going to be the empty set. You can show that by either hitting braces with nothing in it or with that symbol for the null set. If you're doing it in my math lab, use what's appropriate from the choices that they give you. Please realize that if I write it like this set is not empty. You don't want to write it like that. Some people kind of go overboard and say, oh, I'm going to use it. Should I use one or the other? I'll use both. And in using both, you get it wrong. Because do you notice that there's something inside these braces? It's not empty. It's a set that contains the symbol for the null set. Then next place we're going to go are set operations. And the first set operation that we're going to look at is the intersection of two sets. And again, I hope nobody minds. I'm going to take a minute and give you my little kid way of remembering what the intersection of two sets is. And when I think about intersections, a lot of times I think about when you're driving and you talk about an intersection, the intersection is where two roads cross. And so I live near a sort of busy intersection. I live near the intersection of Main Street and Harlem Road in Amherst. Does anybody know where that is?
Yeah, you're just down the road.
Yeah,
I do.
it's just down the road from my house too, real close. And so sometimes I get up real early in the morning when there isn't much traffic and I go for a run. And sometimes I run, not in the middle of the street, but sometimes I run in Main Street. And if I'm over here, I'm in Main Street. Other times I run on Harlem Road. And if I'm over here, I'm on Harlem Road. But if I were to stop here, is everybody all right? Right here, I would be both in Main Street and in Harlem Road. And that intersection would be that piece of blacktop that's common to both. It's what's in both streets. And so when I talk about the intersection of two sets, I talk about the elements that are like that blacktop that are common to both. It's kind of like where the sets overlap. What they share, what they have in common. When I talk about intersection, the symbol for intersection is a upside down kind of elonged, blocky looking view. And so let's say, for example, I have a set A, which contains the numbers 1, 2, 3, and 4. And I have a set B that contains the numbers 2, 4, 6, and 8. And if I look for A intersect B, I'm looking for where those two quote unquote overlap, what they have in common. And does anybody see any elements that are in A that are also in B that are common to both?
4.
4.
Anything else?
Two.
Two. And please notice, when you put elements in a set, the order should not mirror. But I'm going to say that with a little asterisk up above. I put in little asterisks in the air with my finger, by the way. The asterisk is pay attention to the directions when you're putting answers in MyMathLab. While technically with a set order does not matter, every once in a while they get weird and they put in fine print after the question, put your answers in order. So if the directions say to put them in order, put them in order. But if they don't, it should not matter. Okay? So the one operation is intersection. The other operation is the union of two sets. And when I think of the union of two sets, I think of two uses of the word union. I think of a labor union. And with a labor union, it's kind of everybody all together, that idea that there's strength in numbers, that we're taking everybody in. The other use of that word union that I think of is like something sort of like a marriage. It's a union of two people. And when you take that marriage, when you take that union of two people, it's all the first partner stuff combined with the second partner stuff. And so you put it all together. So when I take the union of two sets, I put it all together. I take all the elements from both sets.
Can a union have more than two?
Sure, you can take the union of 3 or 4 sets. You can take the intersection of 3 or 4 sets. It's what those sets, though, have in common.
Okay.
Okay, symbol for union is easier to remember because it looks like a U. It's that intersection symbol upside down. And so if I take those two sets that I defined, pardon me, previously, A being 1, 2, 3, 4, and B being 2, 4, 6, 8. When I take their union, I want everything from A. So I've got 1, 2, 3, 4, and I want everything from B. But you have to remember, there's no need to repeat. And so B has 2, but my set already has 2 in it. I don't need to write it again. B has 4, but my set already has 4 in it. There's no need to write that again, but I do need to add the 6 and the 8. And so I'm taking all of the elements of both. Another symbol that you sometimes see looks kind of like this. It's kind of a funny looking C, and that means subset. We use it to compare two sets. One set is a subset of another. If all of its elements are contained in the first set. So what's that all about? I'm going to look at two sets. My first set is going to contain the numbers 1 and 2. My second set is going to contain the numbers 1, 2, 3, all the way up to 10. Is everybody comfortable with putting that dot, dot, dot in there? Kind of like a little kid saying, skip a few, but we've got the pattern here. And do you notice that both the 1 and the 2 are in that second set? And so I'm going to say 1, 2 is a subset of 1 through 10. It's almost like saying that 1 and 2, the way that looks like a C, it's like saying it's contained in the set 1 through 10. And so it's a way of comparing two sets. If I look at another example, let's say I've got the set 1, 3, 5, and I want to take it intersect the set 2, 4, 6. And so when I take the intersection of those two sets, what do they have in common? Is there anything in the first set that's also in the second set?
No.
No.
Nope.
So that intersection is the empty set. Instead, if I have 1, 3, 5, and I union it with 2, 4, 6, when I take the union, I combine the two, I put them all together. And so putting them together, let's see, I would have 1, 3, 5 from the first, and 2, 4, 6 from the second. So that idea of intersection, where they overlap, what they have in common, and sometimes they don't have anything in common, and union, taking those two sets and just putting them together. So far, so good.
Mhm.
All right. Then next, we're going to look at some special number sets and the relationship between them. The first number set is usually abbreviated with the uppercase N, and that N stands for the natural numbers. And sometimes you see the natural numbers referred to as counting numbers. And I like to think of them as the first set of numbers that you experience as a child when you start looking at numbers and you start counting things. And so when a little kid starts counting, don't you start with the number 1? You've got 1, 2, 3, 4. And as much fun as it is, we could spend the rest of our lives listing them. And so we put those 3 dots, dot, 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 to say that it goes on and on and on. In case anybody's interested, those 3 dots, dot, 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 is called an ellipsis. It just means and so on and so on. Or like in the previous one, we skipped it. Is everybody familiar with the set of natural numbers?
Yep.
Next set of numbers then is W, and W stands for the whole numbers. And can anybody remember from any place in their mathematical career the difference between the whole numbers and the natural numbers? If not, can I give you my little kid way of remembering what I learned a million years ago that stuck like glue? When you think of that word whole, here we're spelling it with a W. But if I took whole and just spelled it with an H, if I asked you to draw a hole in your paper, wouldn't you draw a circle? And that circle looks a heck of a lot like a 0. And so the difference between the natural numbers and the whole numbers is just that it includes 0. It's like there's a hole in the front of the list. There's only one number difference between the two sets, but that number 0 is a really, really, really important number. Later, when we get talking about properties, we'll find that the additive identity, that there's special properties for multiplication by 0. There's special properties for division by 0, things like that. So 0 is a real important number. It's enough to make a difference between the two sets. But as I look at the two sets, does everybody see that every natural number is also a whole number? So we'll be able to say that the natural numbers are a subset of the whole numbers. Next set that we look at is abbreviated with a Z, but it doesn't start with a Z. One that's usually abbreviated with a Z is a set of integers. We use Z and not I because we're going to find that I has a totally different connotation a little bit later, probably within the next couple of weeks. But our integers include our whole numbers and also the negatives, the opposites of our natural numbers. So the integers include the prime numbers. And as I look at that set, does everybody see that the whole numbers are a subset of the integers? Every whole number is in the integers. Next set of numbers are abbreviated with a Q. And as I think about math words with Q, what comes to mind for Q is quotient. Quotient is division, which can be shown as a fraction. Q stands for those rational numbers. And again, that idea of Q being a quotient, being a fraction, as I look at that name rational numbers, I see that word ratio. Rational numbers are numbers that can be expressed as a ratio of integers. Whoops, not ratio, sorry about that, of integers. Which means they can be written as fractions. And so if I try to write the rational numbers as fractions, if I try to put them in an orderly list and come up with a pattern, I don't think it's possible. Because if I look just in between 0 and 1, I could go 0, a half 1, but then there's a quarter. And then between 0 and a quarter, there's an 8. Between 0 and an 8, I could put in a 16. And it gets to the idea that they're dense. To say that they're dense means that between any two rational numbers, or between any two fractions, I can put an infinite number of rational numbers. You can always come up with some other number midway between two fractions. If we just think of taking the average of the two fractions, it would fall in the middle. Because of that property, we cannot use rosters to show it. And so remember we had said that there were 3 ways of showing a set, and the only way that we really used was roster. We need to use another method, and we're going to use something that's called set builder notation. And set builder notation can be used in many ways, but it's most frequently used when, like these rational numbers, there are too many, but we can't list them by roster, and even the ellipsis doesn't take care of it. And so if there's too many values, what I do is I use a variable to represent what's in the set. to represent the elements of the set. And so the way in which I do this is I start with a brace. Then I put the variable. Then Mr. Blitzer in your textbook uses a bar. Sometimes instead of a bar, you might see a colon. And then what follows is a description of what the variable represents. And we close it with a brace. When we read it, we read it as the set of all, and then we put the name of the bar, variable, pardon me, and then the bar represents such that, and then I give my description. So, what's all of this about? My rational numbers, Q, are going to be the set of all x such that, and now we have to say what x is. And we said that the rational numbers are fractions. So I'm going to write it as a over b. But now I have to say what a and b are. So we're going to say that a and b are integers. So a and b are elements of the set of integers. So I'm going to read this as the rational numbers of the set of all x, such that x equals a over b, where a and b are integers. But I have issues. You're going to find during the course of the semester, I have a lot of issues. The one issue that I have is this is here is telling me that a and b can be any integer. And when I look at a fraction, I can put any integer I want in the top, in the numerator. But does everybody remember? We can't put absolutely every integer in the denominator. Because, does everybody remember, you can't divide by 0. So we have to add in there the fact that b cannot equal 0. And so the rational numbers is the set of all x such that x can be written as a fraction made up of integers, but my denominator cannot be 0. And that's what that line of symbols is telling us. And that's that set builder notation. Some of you might have also learned that the rational numbers, those fractions, can be expressed as terminating, which means that they end, or repeating decimal. And so any decimal that repeats should be equivalent to a fraction, and any decimal that ends should be equivalent to a fraction. So, for example, a terminating decimal, I could say that 1/4 is 0.25, and that's all there is to it. When I do that division out of ends. As opposed to a repeating decimal, I could say that 1/3 is equal to 0.333, and it just keeps on repeating. Or sometimes you see that repeating written with a bar. And so our rational numbers that can be written as fractions can also be expressed as a decimal that ends, that terminates, or a decimal that repeats. And aren't all our integers rational? Because any integer can be expressed as a fraction. Just by putting it over 1. Our next set of numbers is defined in a very different way. Rather than saying what it is, we say what it isn't. Our next set are irrational. And our irrational numbers are numbers that are not rational. Just like an irrational person is a person who is not rational. But irrational numbers cannot be expressed as a fraction. There are non-repeating, non-terminating, decimals. And there's some pretty common irrational numbers. Everybody familiar with pi? That non-repeating decimal. And things like the square root of 2 would be irrational. The square root of any number that's not a perfect square would be considered irrational. Another irrational number that's defined as a limit, that if anybody is after this class taking that Math 111, that advanced algebra in 3, you'll run into E, which is Euler's constant. Or if you're ever in a place in life where you need to know about logarithms, you'll be introduced to Euler's constant. Last set of numbers that we'll talk about are usually shown with a really fancy font, uppercase R. They're the real numbers. And they're the union of the rationals and the irrationals. When we take those two sets and combine them. I'm going to real quick add a page if everybody's okay with that, if I turn the page. Sometimes you see a graphic representation of all of this. It's something that's called a Venn diagram, which is just a picture that kind of wants to show you the relationship between sets. And so we'd start with our natural numbers. And all of our natural numbers fall into our set of whole numbers. And all of our whole numbers fall into our set of integers. And all of our integers fall into our set of rational numbers. And all of our rational numbers fall into our set of real numbers. But what's outside of the rationals are the irrationals. Real numbers are going to, for the most part, be all of the numbers that you've used in your life, probably up to this point. A little bit later in the semester, we're going to find that there are some numbers that are not real. If they're not real, we don't call them fake. If they're not real, we have to use our imaginations. So in a little bit, we'll be talking about imaginary numbers. And then when we mix the real world with the imaginary world, our life gets complicated. And so that will give us a bigger set of numbers called complex numbers. How fun is that? The way you're going to see questions on this in the homework, my labs, is they're going to give you a set of numbers. Let's say I have -6, -6/7, 0, 0.25, radical 2, 4.8, and the square root of 49. And they ask you to, from that set, list what fits into each of the categories. So they want to know from that set, which are natural numbers, which are whole numbers, which are integers, which are rational numbers, which are irrational numbers, and which are real numbers. And so let's take a minute and see if we can take those number sets and say which belongs in each of the subsets. And when we do this, it's okay if we use values more than once. So first are our natural numbers, our counting numbers. We're not including 0 or negatives or fractions. Can anybody in this set see a natural number, a counting number? Be careful, you might have to do a little bit of work, a little bit of simplifying. Any ideas?
Seven.
7. So the natural number would be that square root of 49, which is just 7. Beautiful. And then when we go on to our whole numbers, we said that our whole numbers include our natural numbers, pardon me. So that square root of 49, it's going to be in there. And what do we have to add to make the whole numbers? What can we add to make the whole numbers?
0.
0. Then our integers include our whole numbers. So our square root of 49 is in there and our 0 is in there, but we're also adding our negatives. And so wouldn't we add the -6? Then with our rationals, we add our fractions, our non-repeating, I'm sorry, our terminating, I apologize, our terminating and our repeating decimals. So they include our integers. So they have that radical 49, that 0, that -6. And that's what this, I don't mean to make you seasick, I'm gonna speed up for a minute. That's what this means over here. We're saying that everything that was a natural number is a whole number. Everything that's a whole number is an integer. Everything that's an integer is a rational. And so my rationals will include those plus my fractions. So that's the -6/7, the 0.25, and the 4.8. Now, irrationals are defined as what's not rational. So I'm going to look at this set and compare it to my original set and say, what don't I have in there? Got the radical 49, 0, the -6, the -6/7, the 0.25, the 0.48. Does everybody see what's excluded is the square root of 2? And so that's my irrational. And then at this stage of the game, where we are right now, all numbers are real. So when I look for the real numbers, I'm going to include absolutely everything that was in that original set. Again, order does not matter, but I'm going to put them in the order in which they were all originally written. So far, so good. Does everybody feel like you could do that? I think there's a couple of questions like that. If so, I'm going to turn the page. And the next place we're going to go, whoops, talking about real numbers, is the real number line. And I think, can I assume that everybody in the class has seen a number line drawn? They should be straight, but obviously I'm not taking off for artistic merit because mine isn't. You usually label them with your integers, which should be evenly spaced. And to show that it's an infinite set, we want to make sure that we put arrowheads on either side. So it's infinite. We should have some semblance of equal spacing between the integers. But what's cool is it's a long, mathy sounding sentence. There is a one-to-one correspondence between the real numbers and the point on a number line. There is a one-to-one correspondence between the real numbers and the points on the number line. So that's a mouthful. What does it mean? It means that absolutely every real number can be represented by a point on the number line. Over here, somewhere between 3 and 4, there will be a point for, oops, I can't draw it here, for pi. Somewhere between 1 and 2, there will be a point for the square root of 2. And in between, the way lines are made up, they're made up of an infinite number of points. And so there's an infinite number of little dots in between. And every dot will also have a number named for it. Every point will have a number for it. Every number has a point. Every point has a number. And part of what we use that number line for is we use it to order numbers. And when I talk about ordering numbers, that's when I bring up my symbols of inequality. And for symbols, do they look familiar to you folks?
Yep.
This first one, when I look at this first one, it sort of looks like a crooked L to me. And the fact that it's a crooked L reminds me that that's less than. And we're going to define if A is less than B, then A is to the left of B on the number line. And so next symbol, if I reverse it, the opposite of less than would be greater than. And we're going to say that if A is less than B, then B is greater than A. Next one looks like my less than symbol, but somebody drew an equal sign at the bottom. And so this one's going to be less than or equal to. You realize that's an or, not an and. We can't do both at once. Then we can either be one or the other. And in the same way, this next one is greater than or equal to. And as we go until 45 or 50? Do I have
45.
45?
Yep.
Okay. So I'll tell you what, because it's Friday and everybody's ready for a weekend, I'm going to just go with the 45 and not double check. And so also in terms of where we're going next, this is a logical place to stop. This is the next concept, the idea of showing inequalities on the number line and using them to come up with interval notation. Will probably take more than 5 minutes. So we'll stop here. I'm going to, whoops, stop sharing my screen if that's all right with everybody. Stop recording.